Hi, my name is Hayden Webb. I'm an undergraduate from Rice University, and I will be presenting my project on the Wearable roller rings to enable robot dexterous and hand manipulation through active surfaces. Before we get into the device, I'd like to give a brief introduction to the field itself. So, we as humans inherently know that power and precision graphs enable us to manipulate objects in different ways, i.e., there exists a trade-off between stability and manipulability whenever we grasp objects. And robots experience the same discrepancy whenever they manipulate objects in these graphs. So naturally, this begs the question of how do we overcome these drawbacks? So I like to answer this with a metaphor. So primitive man going from mountain A to mountain B would take 5 days. And they said, well, okay, I want to do this faster. So they tamed the horse, and this took 3 days. And they're like, well, that's nice, but I'd like to do this trip even faster. So did they add legs to the horse? No, they invented the wheel. And that is where I'd like to segue into the idea of active surfaces. These are rolling components that they contact with a grass object and physically manipulate it through its actuation. And we see this in everyday life. It can be spheres, belts, bearings, anything where its rotation causes some form of translation. And we can see that robot hands that integrate these ideas or these active surfaces can overcome the previously mentioned grass discrepancies to have high levels of manipulation. However, these designs have them integrated internally and are not generalizable. Furthermore, the algorithms designed for these systems are created in this similar ad hoc manner, meaning I cannot transfer them from the device to an already existing device itself. And that is where the roller ring comes into play. So we can see it here is made of two very simple subsystems. We have the conformable affixing sleeve module of the chasm, which allows it to affix to any end effector that is on an angle guide track to help generate differential motion, as well as a routed active surface controlled by an actuated micro DC motor. And so to create this level of manipulation, we first started off with the idea of the unit sphere model, using the very simple idea of if I have some torque A and some torque B, I can use their different weights to generate some resultant torque. And this is very easy for objects of non-variable geometry. As you can see here, we're able to generate roll, pitch, and yaw for a unit sphere, as well as translate an object in hand. But life does not always exist with non-variable geometry. And so we developed the multi-sphere model as well, using the difference in radii as a weight for these torques. We can take objects of non-variable geometry and manipulate them in hand. And this goes further beyond the robot hands already shown. We can augment both human and robot hands to achieve this high level of manipulability. So the roller ring addresses issues found in the previous active surface designs. As seen, it can be affixed to any grasping system through this chasm. More so, the developed motion model can be generalized to any active surface grasping system, and it is generalizable to any number of roller rings to generate some high level of differential manipulation. While there are constraints in the size of the object, as well as the scratching from the angle put into this and lack of compliance, we're currently working on ways to work around this by having high level compliance on the front, more closed loop algorithmic approaches to generating these motions, and much more to improve this. And so I'd like to give thanks to the members on my team, as well as the Rice Engineering Computer Science, as well as the Oshman Engineering Design Kitchen for their help in facilitating this project. And with that, I'd like to leave this summary for y'all. If you have any questions, please come find me at the following poster session. I thank you for your time, and thank you once again.